We're starting. So welcome guys. Welcome to our third lecture in our quantum mechanics and or essentially our high energy physics series. I'm very excited for this one. We have six speakers here. It's going to be a very long one. So essentially we can go to the abstract. I don't want to chew time through. Yes, so in this talk we'll mainly explore the relationship between non-relativistic quantum mechanics and particle physics. So that will be handled very professionally by Raguveer here. And we'll start from the very basics, understanding the Schrodinger equation in spherical coordinates. And by that, we do assume that the listeners or the audience have some clue about what the basic Schrodinger equation is, because you can't bother to know the spherical coordinates without the Cartesian Schrodinger equation. And we will also discuss two particle bound states, the hydrogen and positronium and quarkonium bound states. And we'll finally end the talk talking a little bit about mesons, baryons, and their magnetic moments. So, yes, Gavin Paul will be talking first about Schrodinger equation in spherical coordinates. So, I'd like to hand the floor over to Gavin Paul.
Yeah,
Yep.
so I'll be talking about the Schrodinger's equation for central potential. Basically what Rishi said, Schrodinger's equation in spherical coordinates. So first we'll start off with the Schrodinger's equation in Cartesian form, which you can see right in front of you. IH cross dou psi by dou t, which is equal to minus h cross by 2m del square psi plus v psi, which is Schrodinger's time-dependent equation. And delta squared here is a Laplacian, which is dou square by dou x square plus dou square by dou y square plus dou square by dou z square, which is basic. We should all know that by now. Okay, so first thing we need to know is that the probability of finding the particle in all of space has to be 1 because it has to exist. So therefore, dou psi of dx cube is equal to 1. So and dx cube is a all space. So it is dx into dy into dz. Next slide. Okay, so now we're going to separate the variables here. So as a function of position and a function of time. So here we put psi of x comma y comma z into f of t. So separating position variables and separating the time variable. So the Schrodinger's time-dependent equation can be written as follows: 1 by psi into minus h cross square by 2m del square plus v into psi, which is equal to I h cross by f dou f by dou t. Next slide. Okay, so the only way that this equation can be true is if both sides can be are constant. So this constant is the total energy of the system. So we're denoting it as E. So equation 3, that is what we just found, is written as minus h cross square by 2m del square plus v psi, which is equal to E psi. Now you might notice that this equation looks very familiar. This is Schrodinger's time-independent equation. Okay, so then continuing onwards, we have on the right-hand side IH cross by F dou F by dou T, which is equal to H of F. Now the solution for the fifth equation is very simple. It's just F of T is equal to e to the power minus I E T by H cross. And next slide. Okay, so now we're looking at equation 4, that is Schrodinger's time-independent equation. It's just h psi, which is equal to E psi. There's nothing to it. So now we're substituting that f of t in the place of, we're substituting e to the power minus I E T by h in the place of f of t in equation 4, I believe. Okay, so now we've done Schrodinger's equation in Cartesian coordinates. So now we'll have to change it to spherical coordinates. So next slide. Okay, so in Cartesian form, del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. But in spherical coordinates, it becomes a little bit more complicated. It is del square is equal to 1 by r square into dou by dou r into r square into dou by dou r. Which we can separate even further than before by putting r of r, theta of theta, and phi of phi. Next slide. Okay, so now equation 4 just reduces to 3 ordinary equations. 1 by r square, dou by dou r into r square, dou by dou r, which 2m by h into v of r minus e into r. Now, L is just the azimuthal quantum number, which you guys should know already. So continuing on, then sine theta dou by dou theta into sine theta dou theta by dou theta, which is equal, that theta should actually be in the denominator there as dou theta, but okay, which is equal to m of L square minus L into L plus 1 sine square theta into theta. And dou square phi by dou phi square is equal to minus ml square phi. Okay, so now equation 9 is basically the radial part of the equation, which is what we need. But before we talk about that, we'll first look at the equation 10 and 11, which is the angular part of the central potential. Next. Okay, so solution to equation 11 is again easy. So phi of phi is simply e to the power I of ml phi. But the solution to equation 10 is a little bit more complicated than that. It requires the associated Legendre function, where the final answer is theta of theta is equal to p of L mi cos theta, where if you're interested, p of L of m of L of z is equal to 1 by 2 to the power L into L factorial into 1 minus z square to the power m of L square into dou by dou z to the power L plus ml into z square minus 1 to the power L. Okay, so we found theta and we found phi. So generally, if we want to get the spherical harmonics, we need to combine both theta and phi. Okay, so if we combine them both, we get equation 14, which is y of L m of L theta comma phi is equal to root of 2L plus L by 4 pi into L minus ML by L plus ML factorials into minus 1 to the power ML t to the power ML cos theta e to the power I ML theta. Okay, so next slide. So these are some examples of spherical harmonics which are already solved for values L is equal to 0, L is equal to 1, and L is equal to 2. Now, as you guys might know, the values of M are from minus L to plus L, which is why there's an increasing number for each and every one. We're only concerned with the spherical ones though, so Cartesian and rotating is there for your own perusal. Next slide. Okay, now to the main part, which is the radial equation. So equation 9, which was the radial part of the Schrodinger equation, is simplified by introducing the new function u of r is equal to r into r of r. So equation 9 becomes minus h cross square by 2m into dou square u by dou r square plus v of r plus h cross square by 2m into L plus 1 by r square of u, which is equal to E of u. Okay, so this equation is the radial Schrodinger equation, and it has the same form as Schrodinger's time-independent equation in one dimension, except that the potential part is has an extra part to it called the centrifugal barrier, the h cross square by 2m into L plus 1 by r square. Next. Okay, so while we're solving the radial equation, we find that only certain values of E lead to acceptable results. So I mentioned from the beginning that the probability of finding the particle should be 1 in all of space. So only certain values of E lead to that probability being 1. So only those values are acceptable. So this led to one of the most important discoveries in quantum mechanics, which is a bound system can only have energy of specific values. So now handing it over to Rishi, who's going to talk about the energy level of hydrogen. Or, sorry, Raguveer.
No, it's Gavin after us. Yeah, you totally forgot. Sorry, Raguveer. Yep, go on.
Okay, so in this section, we are going to see about the Klein, Gordon, and Dirac equations. So next slide, please. So what is the Klein, Gordon equation? So like the Schrodinger equation that Gavin mentioned, Klein, Gordon equation is also a wave equation, but it is for zero spin particles, and it is a relativistic quantum equation. So why do we need such an equation? So as I just said, Schrodinger's equation was for only for non-relativistic particles, and you can as if as and Schrodinger's equation basically represents this equation below. So if you replace the classical observables with the quantum operators, you get the Schrodinger's equation. And this equation is it's not Lorentz invariant, and although it has both derivatives of space and time, there are two spatial derivatives but only one time derivative. So that was the problem. So next slide, please.
Bolon?
Yeah. Someone said hold on.
No. Please go on. Please go on.
Okay. So what did Klein and Gordon do? So what they did was they developed a relativistic energy. They developed a quantum mechanical relativistic equation from the relativistic energy momentum relation that was given by Einstein, which is this equation 16. So if we substitute energy here, E is energy and P vector is just Px, Py, and Pz. When you substitute these for their respective operators, you get equation 17, which is given at the very bottom. We'll just pause for a bit. So this is essentially the Klein-Gordon equation. So what this does is once again. Yeah, so what this does, and an important point is that the wave function phi of xt here can also be called as a field, because the arguments x bar is just x, y, and z. We're just representing it as x bar, and x bar sorry, the arguments of phi extends all over space time, so it can be considered as a field. So so another way to say this is that the Klein-Gordon equation describes the fluctuations of the field that is defined by phi of the field is phi. So how it fluctuates, that thing is described by the Klein-Gordon equation. So this was the first attempt at a relativistic quantum mechanical equation. Next slide, please. Yeah, this is what. So as you can see in the equation here, we have just written the same. This is the same equation, but we have written it in natural units, which means that we choose units for these variables such that h bar and c always are always one. This is just a shorthand writing for this. So this is the Klein-Gordon equation. Next one, please. So the Dirac equation. The Dirac equation is very similar to the Klein-Gordon equation, but it describes the fluctuations of a field where the spin of a particle is half, 1 by 2. This is very useful because in particle physics, most of the particles we deal with are of spin half. So what Dirac did was he started his equation from the same Einstein energy momentum relationship, but this is written in natural units, so don't forget the h's and the c's there. So if you want to get the h's and c's back, you can do a dimensional analysis and you'll just get them back. So now we are going to talk about four vectors. Four vectors is nothing but so p mu. P mu is a four vector in the sense it has one it has four components. One of its components is temporal component, and the other three are spatial components. The temporal component here is defined by E over C, but we can consider it as just E because as I said, in natural units, C is equal to 1. And P vector, again, it's used to represent Px, Py, and Pz. So when you take the dot product of this four vector, this is the equation you end up with, E square minus P square. So you can replace P mu and the dot product of this four momentum vector in the Einstein energy relationship. So next slide, please. So this is the equation you get. So I'll be referring to this as the original equation for our convenience. And so as you can see, this is still what do you say? This is still a second order differential, which means that when you apply this to a field phi, you won't be getting what do you say, a uniquely defined value for phi. So what we need to do is we need to factor it and get a single derivative equation. So normally when you have an equation, say x square minus y square, you take we factorize it like x plus y into x minus y. But in this case, you can't do that because p mu is a vector, whereas m is just a scalar. So you can't add or subtract scalars and vectors like this. So what we do is we contract the four momentum vector p subscript mu like so, using arbitrarily defined four vectors, which are alpha and gamma. So contracting just means we are multiplying this with two vectors so that these become a scalar. That's all. Or in essentially so that we can subtract it or add it with a scalar. So now what we're going to do is that we're going to set special conditions for alpha and gamma as we go, so that when you open the brackets of this equation, you get the original equation. Okay, so that we know that this form of factoring is correct. Okay, next slide, please. When you open the brackets of the first equation, you get the equation at the top of the page. So as you can see, we need m square should remain, and we need to eliminate the cross products here, which are m alpha nu p nu and m alpha mu p mu. Sorry, gamma mu p mu. So the first condition we set is that alpha mu is equal to gamma mu. This is just like saying that alpha and gamma, which we used in the previous equation, are just the same four vector. So alpha 0 mu is just indices, right? So it will be from 0 1 2 3 for all the four components. So this is just saying that alpha 0 should be equal to gamma 0, alpha 1 should be equal to gamma 1, like that. So after we set this condition, for the middle terms will get cancelled. So the equation we left it is this: gamma mu p mu minus m square equal to 0. Now this is still not the original equation. So let's just expand this term and simplify it. So expanding this term in the sense, this is just summing over, right, in Einstein notation. So we have gamma 0 p0 plus gamma 0 gamma 1 p0 p1 and so on. Like we have a bunch of terms. So in that we can group all the like terms together and represent it as a summation as the first term in the next equation. So sigma of nu comma v gamma comma mu comma nu gamma nu. So yeah, the first term. If we say lots of mu's and u's, it will be confusing. So the first term is we have expanded this, and we have grouped the like particles. So the remaining are the unlike particles. So these are particles for which mu and nu are not equal. So p naught and p0 and p1 are just variables, so we can interchange them, so it doesn't matter. So now what we need to do is we need to eliminate all the unlike terms, and also to get the original equation. If you go back and see, you will see that there is a contravariant vector p superscript nu dot p subscript mu minus m square. So the condition we set should be in such a way that gamma nu gamma mu should be equal to a metric tensor, so that when you multiply it with p subscript nu, you will get a contravariant vector. So this is a very elegant condition. this relationship here defined between gamma nu and gamma mu is an anti-commutator relationship. For example, we have seen commutator relationship where if a comma b commutes, that means ab minus ba should be equal to 0. Like that, anti-commutator means ab plus ba should be equal to 0. Now this is not possible for normal numbers. So from that we can infer that the components of the gamma vector are matrices. We can easily show two matrices that have the relation AB equal to minus BA or AB plus BA equal to 0. So that's what we've done here. So how this term, so as you can see, when nu is not equal to mu, so when the, so if you recall the metric tensor, you'll see that it is just a unit matrix, right, in 4 dimensions where the signs are a little different. So essentially only the diagonals are the value. That means when it has only if you take the notation plus minus minus minus, the first term is +1 and the second one is minus and all the other ones are minus. So you can see that whenever mu is equal to nu, it has a value. For anything other than that, it goes to 0. So essentially what this is saying is when mu is not equal to nu, that is for all the unlike terms, this inside the brackets sum will be 0. So we have eliminated the unlike terms. So the next part I need to express this gamma mu as a metric tensor. So how we do this is gamma, when nu is equal to mu, gamma mu is just gamma nu, it's the same thing, right? So when we add that, we can write 2 gamma mu and the 2's get cancelled, so it becomes a metric tensor. So when you multiply that metric tensor to p nu, this is the final equation we get. So keeping in mind these two conditions, we have seen that this form of factorizing is correct. So next slide please. So factoring again, we have this equation. So the minus, conventionally we take the minus term to be c0. So that's what we've done here in the next part. And so now we are going to take this. Now this is a classical observable. So now we are going to take this as a convert this into a quantum operator. We know that the contravariant vector p mu is e comma p vector. No, so when we substitute the operators, we get this equation. So also, like I said before, this is the, when you want to convert a contravariant to a covariant vector, you multiply it with a metric tensor. So when you do that, as I said, next slide please. Yeah, so we're using the metric tensor of form plus minus minus minus. This means that the space term will retain its sign, whereas this sorry, the time term will retain its sign and the space term will like, get a minus sign. So as you can see, the covariant form of this mu vector will have this, and further we can write it shorter as dou nu, where dou 0 represent dou by dou t, dou 1 will represent dou by dou x, and so on. So in substituting this back in the original equation, not the original equation, uh, in the gamma p equation, we get this final equation. So this is the Dirac equation. Now I won't be going into the consequences of this equation because we need to understand spinors and all that stuff before going into the consequences. So we'll be seeing the consequences in the further lecture. So for now, this is the Dirac equation, and it's a very important equation because it helps us a lot in when we are dealing with problems, when you're dealing with particles with half a spin in particle physics. Thank you.
So, okay, I'll be taking over from Raguveer right here. So, my slides of interest will be about the hydrogen atom and its fine structure. Okay, so go on to the next slide, Pugal. Yes, so we know that the most basic atomic structure is of the hydrogen atom. Right? It consists of an electron orbiting a central proton. So, Pugal, go to the next slide. This is just like a, yes. So why do we call the proton to be centralized? We say it to be central because of the huge difference in masses between the electron and the proton, which I'm sure we all know about. So it can be said to be at the origin and the wave function to be investigated right here is of the electron. Okay, the potential energy of the electron due to the attraction of the nucleus is given by the following expression. Right? The potential energy of the electron is given by V of r equals negative E squared by r. Yes. So Gavin previously went through deriving the radial wave equation, so I'll just skip over that. So now we need to substitute for this potential Vr in the radial wave equation we derived from the Schrodinger's wave equation in the previous section. So we can collect that the radial wave equation is of this form of equation 19. I'm not going to even try to read that because it's a mouthful, so you can just take a close look at that, and we'll go to the next slide. Yes, so also again, thank you, Gavin. So we know that when the potential is substituted into the radial wave equation, right, we see that the only normalizable solutions occur when E assumes one of the values, right? One of the values of here that it's mentioned here, E of E underscore n is equal to negative me squared by 2 h bar squared n squared is equal to negative alpha m c squared into 1 by 2 n squared is equal to negative 13.6 electron volt by n squared, where n to be noted here is 1, 2, and 3. Right? It cannot be any other half integer. And alpha right here, take a very close look. The alpha right here is represented by e squared by h bar c is equal to 1 by 137.06. This is obviously found from experimental results because you can see there are a lot of decimal points and all. Yeah, this is called the fine structure constant. Okay, so yep, go on. Next slide. So yeah, from the previous equation right there, my numbering is a bit messed up there. Do not take that into consideration. So from the previous equation or the radial wave equation, we can obtain its corresponding normalized wave function to be this behemoth here. Okay, and as of the radial wave equation, I'm not going to attempt to read this out. You can just read this out yourself. Where this a right here, the 2 by Na, that a right there, is the Bohr radius of the hydrogen atom. It's given by h bar squared by me squared is equal to 0.529 into 10 to the power minus 8 centimeters. Okay, and that L right there, that L 2L plus 1 and the subscript being n minus L minus 1, we'll look at what that is in the next slide. It is, yeah, go down. Yes, so this is just a very small mathematical interlude, right? This LP Q minus P of Z is called the associated Raguveer polynomial. Okay, so this is essentially the solution for the second order linear differential equation of the form of equation 23 right there, xy power n plus 1 minus x y dash plus ny equals 0. If we go to the radial wave equation, right, we can see that it's of this second order linear differential equation. So we'll get its own Laguerre polynomial, and then we need to substitute that into our wave function for us to get our eigenvalues and eigenstates. But a very important point to note here is that if we go on to the next slide, is that, yes, wait, go back. I think you skipped a slide. Okay. Yes, go on. Yeah. So here's the deal. So now that huge wave function that we saw previously is not of interest to us, and because it's huge and there's a lot of terms in there, and then it's going to take a lot of effort to like dissecting that. But what we can infer from that is the energy degeneracy level or information that it contains. So we see that the wave function is labeled by three numbers. If you go up, like go up back to the wave equation part, 2 slides up. Yes, right there. Yeah, go on. Yes, we see that the wave function psi is named by n, L, and mi. Right. So what are these three numbers? So the n is obviously the principal quantum number, which tells us the energy of that state it's in. The L being an integer from 0 to n minus 1, and what does that do? It gives us the total orbital angular momentum, and mi ranges from -1 to +1. So what is that? It's a component of angular momentum. So we can see how the wave function contains a lot of information about the states of that electron. Okay, so now inspection, close inspection tells us that there are, okay, this might be a mouthful, but just listen to this. There are two L plus 1 different MIs for each L and N different MIs for each N. So I think I will say that again. So there are two L plus 1s for two L plus 1 different MIs for each L and N different Ls for each N. So the total number of distinct states we have here that share the same quantum numbers, uh, quantum number n, and hence the same energy level is, go down 2 slides, Google. Yeah, so the degeneracy of the nth energy level is given by this equation right here. Sigma summation to n minus 1 L equals 0. 2L plus 1 is equal to n squared. So that was what I essentially tried to put it in words, which could be successful if you listen to it carefully, but this is all you need to know. This, we infer this information directly from our wave function. You know, we are not um, concerned about any other things right there. Okay, so we'll come back to this graph right here, or this diagram right here. So we'll go down and then we'll return back there quickly. So yeah, yes. So now we see here that the hydrogen atom is highly degenerate. Okay, what do I mean by degenerate? Its spherical symmetry dictates that the two L plus 1 states with a given value of total angular momentum should be degenerate. Okay, since they only differ in the orientation of L. But what does this suggest? This inherently suggests that a sequence of 1,1357 of the principal quantum numbers um, do this, and whereas the energy levels of the hydrogen must have much higher degeneracies. Okay, so yep. So one thing to note here is that I'd like to make the small point is that while deriving this entire formula for the spectrum of hydrogen, we are completely neglecting the electron spin and relativistic effects, which will be the next section. Okay, so these corrections further emphasize the extra degeneracy in the energy levels, splitting the Bohr energies into groups of closely spaced levels. Okay, so which will be splitting our already existing spectral lines into more distinct values. Okay, so next we see how these quantized values manifest themselves in our laboratory, right? So from Planck's formula, we get our E photon is equal to h nu is equal to E initial minus E final is equal to me power 4 by 2h bar squared, and 1 by ni squared minus 1 by nf squared. Ni and nf is the initial and final principal quantum number states. Okay, so as let me get back to my previous point. How do we measure these quantized energy levels is of question here. Okay, because we can't just measure the direct energy levels of the hydrogen of the electron themselves, because that will be ridiculous. But instead we measure the wavelength of light emitted when the electron makes a transition from a higher level to a lower level, or when a photon is absorbed and it goes from a lower level to a higher level. We must have seen this in a lot of experiments. We must have come across this in a lot of chemistry applications, a lot of physics experiments. So yeah, so yes, we have this entire Planck's formula, and the emitted wave is then given by 1 by lambda equals r into 1 by nf squared minus 1 by ni squared. Okay, so we are essentially just getting it from the basic um, uh, frequency to wavelength relation here. So it's not a huge calculation. You can try that yourself. Where r right there is me power 4c by 4 pi h cube. Okay, so what is this called? This is the infamous Rydberg formula for spectrum of hydrogen. Okay, so let's see an application of this whole equation right here. If we go up to the graph there, we can see the entire spectrum of hydrogen. Go up, I think the previous slide has our, yes, this diagram right here. So we see what's called the Lyman series, the Balmer series, and I don't even know how to spell that. That's the bracket series and the Plund series. Yeah. So essentially, we get these from substituting in the initial and final principal quantum numbers. So either 1, 3, or 4, and then we get our respective energies and our entire Lyman series. So we see how our Rydberg equation is of great use in essentially investigating the entire spectrum of our hydrogen, and which directly shows us the energy level of the electron. Go down. Yeah. So go up to all the way up to fine structure. Go down, go down. Oops, you went up. Yeah, one more slide down. That's just a title slide. Yeah, so as I mentioned before, now we begin to closely investigate the relativistic effects and the effect of spin of the electron itself, how the entire effect manifests itself in the entire structure of the hydrogen atom. Okay, so upon experimental observation, obviously, we saw that the result greatly deviated from the Rydberg formula when spectral lines resolved into doublets and triplets. What do I mean by that? They split it into either two or more lines. Okay, so then hence this entire question of, okay, maybe there's something more into this, and we then the entire concept of our fine structure came into play. So how do we tackle this problem? We call upon the very tried and tested perturbation theory. Me and Pugal have plenty of notes about that. We'll share. Uh, we'll be sharing that soon. So when we make a small perturbation in our Hamiltonian, as in our delta H, right? Sorry, our H, it becomes our new delta H, so that our new Hamiltonian becomes H plus that change delta H. We displace the energy levels too, obviously, because our Hamiltonian is the measure of the total energy in the system, right? So to approximate how much this change in our Hamiltonian results in the direct change in our energy, we can directly just take this entire result right here, which is delta Ej equals our expectation value of our perturbed Hamiltonian, and which is just the expectation value of our change in Hamiltonian. And this is called our perturbation theory. I'm not gonna delve too deep into this because we're a little short in time. Okay, so now we come up to the relativistic correction. Okay, so first we use our relativistic equation of momentum instead of the classical equation in our Hamiltonian. Okay, so T relative is equal to root of p square c square plus m square c power 4, which minus mc square, which essentially boils down to p square by 2m minus p power 4 by 8m cube c square. We see that the first term here is just our non-relativistic momentum, and the second part is where the entire correction comes in play. We'll look into what that implies in the next slide. Over. Yes, so the Bohr energy levels actually go in. Okay, so now we're going to come up to our relativistic correction to Hamiltonian. Okay, so yes, remember when I said that the first term there was just our normal Hamiltonian because it was not relativistic, and our second one was the relativistic correction that we need. So the H relative right there is our negative 1 by 8 m cube c squared p power 4. Now this is the correction that we need for to us to derive the entire fine structure of the hydrogen. So to get the expectation value of p power 4, okay, we use p squared by 2m equals en minus v. Okay, so thus substituting this into equation number 30, we get delta E relative is equal to negative 2mc squared, and then this term right here. So go down. So yes, so we see here that since v equals negative E squared by r, because it's the potential for the electron, we can calculate the expectation values of 1 by r and 1 by r squared. Okay, this is another really small what do you call relation that you is the result that we get in quantum mechanics. I'm not gonna again expand on that, but all we need to know is that the expectation value of 1 by r is 1 by n squared a, and 1 by r squared is equal to 1 by l plus 1 by 2 n cube a. So when we substitute that back into the previous equation, we get delta E relative is equal to this entire term here. Okay, so this is our this is our relativistic correction for our fine structure. Okay, the Bohr energy levels actually go in the powers of alpha squared mc squared when the relativistic correction um, carries two or more powers of alpha as seen here, because we have alpha squared there. Now here we have alpha power 4. Okay, so what do we imply by that alpha power 4? It's very minuscule. It's about 10 to the power minus 4 in magnitude. So it is a very relatively it's a small correction, but this phenomena right here does directly influence our spectrum lines, and that is why we are doing this entire relativistic correction. Okay, so if we go to the next slide, we'll be talking about spin orbit coupling. Okay, so for spin orbit coupling, we first establish the components of the individual effects from the entire spin and orbit coupling, because the electron does have the spin momentum and the spin angular momentum and the orbital angular momentum. Okay, so from the electron frame of reference, okay, the proton seems to be circling around the electron. Hence, this orbital motion creates a magnetic field at the center given by B equals EV by CR squared. Okay, so now this is very simple. Just expressing this in terms of orbital angular momentum is equal to L equals RMV. We get this equation. Okay, our equation 37. And a spinning electron also consists of a tiny magnetic dipole. Okay, then this dipole moment is given by mu equals negative E by mc s, where s is your angular momentum. Sorry, yeah, it's the angular momentum. So, and the energy of magnetic dipole is given by from classical mechanics to be W equals negative mu dot B. So remember, what we are trying to do here is we are trying to measure the change in Hamiltonian and hence the change in our energy levels. So, and hence we right here computed the energy of the magnetic dipole. So yeah, go down. Yeah, so using equation 21, we get the total, the Hamiltonian for spin orbit coupling to be this HSO is equal to E squared by 2m squared C square R cube into L dot S. We are just substituting if you go up, we can just show them that. Yeah, we are just substituting these two quantities in equation 39. Okay, but then there is a factor of 2 introduced in the other thing. Go down. Yeah, so how do we come across this, right? So we know that the electron is not an inertial frame because it's a circular motion, right? So to make this work, we need to speak of an instantaneously co-moving frame of the electron. Okay, so that's a lot of words. So in a sense, it's an inertial system whose velocity coincides with that of the electron at a given moment. Okay, so this then allows us to regard the motion of the electron as a continuous succession of infinitesimal Lorentz transformations as we move from one frame to another. So this procedure leads to this name called the Thomas precession. Okay, so which involves a lot of SR, as you can say, an infinitesimal Lorentz transformation, and it probably involves a lot of SR. So we'll skim it down. So for context, all it does is it introduces a factor of half in our Hamiltonian equation. Okay. So yes. So we know that the total conservation of total angular momentum, we know that the only angular momentum is conserved in spin orbit coupling and not L and S separately. So knowing that J equals L plus S, squaring on both sides gives us this equation. J squared equals L squared plus S squared plus 2L dot S. So go down. So it's continuing from where we left off. We know that from addition of angular momentum, which Pugel discussed in our previous lecture, which you can take a look at. So that a measure of L squared always gives a number of a form L into L plus 1 H bar squared, and the measurement of S squared gives equation 43 as a number. Right? So using both equation 42 and 43 in equation 41 gives us um, L dot S, rearranging that previous equation. L dot S equals this expansion right here. So where J, L and S are quantum numbers describing total, orbital and spin angular momentum respectively. Okay, so we know that spin is half for an electron. Go down. Delta SO equals alpha power 4 mc squared, and then this fraction right here. Now simplifying this equation right here, knowing that J can only be L plus 2 or L minus 1 by 2, because the spin of an electron um, is a 1 by 2 half spin. So we get our final energy value here, delta Fs equals negative alpha power 4 mc squared 1 by 4n squared into this fraction right here. So notice that this equation right here has the same order as the relativistic correction, right? If you recall, it is alpha power 4 mc squared, even though the entire physics of both of these relativistic and spin orbit coupling being different. So now we see the entire significance of alpha as being the fine structure constant. Okay, and how do we get our final fine structure? We combine both our relativistic correction and our spin orbit connection to get our entire spectrum of hydrogen as we see right here. Okay, so yes, so I'll be concluding my part here. I'll be handing it over to Pugal, who will be talking about hyperfine structure and Lamb shift. Pugal?
Audible. Okay, cool. Uh, Let me get started with the lamp shift. Alright, so what on earth is this whole phenomena of a lamp shift? It's actually a very interesting feature. Alright, so the story is that there was actually a very different experimental result, as it always starts in this case, in this field. So essentially, we expected these states, 2 S half and 2 P half, to be perfectly degenerate, but turns out they were not degenerate. They were not sharing the same energy levels, and in fact there was a small shift in the energy levels, and it was this shift that was dubbed the Lamb shift, and it was later explained by several people, especially the founders of quantum electrodynamics, Bethe Feynman, uh, Dyson, and Tomonaga. But anyways, it's to put it in a very succinct sense, it's a correction that comes from relativity, and it's a correction which also comes from quantum electrodynamics. It comes from the quantization of the electromagnetic field itself. So we'll not be diving too deep into it right now, but let's just have a simple review of it. So essentially, this is the gap that was observed. Why is there such a split for energy levels that were supposed to be degenerate, was the question, and the answer came in the form of quote-unquote radiative corrections. Well, these are corrections that come from quantum electrodynamics when we quantize the electromagnetic field itself, and these are just 3 diagrams that represent different radiative corrections. Let me just walk you through them. The first diagram is basically what's called pair production or vacuum polarization. All it does is there's a pair being produced, a pair of particles and antiparticles, in this case a electron and a positron, produced in the neighborhood of a nucleus, and this creates a partial screening effect of the proton's electric charge. So yeah, that's exactly what's going on here. And in the second diagram, what happens is that the electromagnetic field has a non-zero ground state, and this non-zero ground state is basically expressed by the emission and getting back to the ground state itself of a particle. And the third diagram basically has a small, it does nothing but leads to a very small modification of the electron's magnetic dipole moment. To put it in terms, it's a addition of 1.001 to its dipole moment. We'll not go into depth, but we'll consider two cases that will actually show what's going on. So for L equals 0, the lamp shift is given by this equation, equation 48 right here, where k n, 0 is essentially a numerical factor defined as 12.7 when n is equal to 1, and as n asymptotically approaches infinity, we get 13.2. For L equal to 0 and for our j being modified a little bit, that is, I'm not assuming any spin, but I am assuming orbital angular momentum a little bit. What happens is it changes quite drastically, and this is the distinction. This is what causes the shift. And k also, which is a parameter, changes a little bit. It reduces to less than 0.05 rather than being 12.7 or so, and it changes a little bit with its arguments n and l as well. Okay. And another interesting effect that's quite similar but not the same is the Zeeman effect. And you basically get the Zeeman effect when you place an atom in a uniform magnetic field, which we will presume to have a strength B external. This is the B external, and it basically shifts the energy levels a little bit. And the shift is known as the Zeeman effect. And there are different kinds of it, and we'll see how this works. So essentially, I'll start with this is the Hamiltonian, which I need to add to make my correction, and this is called the Zeeman Hamiltonian, or HZ as we'll refer to it. It's basically the sum of the magnetic moments of the dipole moments, the magnetic dipole moments of the electron spin and the orbital motion with the product of the external field. And we know that these can be expressed in this way from what Rishi just mentioned, and we just got to substitute it, and we can see that you'll get a L plus 2s kind of term. Before I even go any further, there are three different kinds of Zeeman effects. So you got the strong field, weak field, and the intermediate one. You get the strong field, that means the Zeeman effect dominates and the fine structure basically becomes a perturbation. Whereas if the weak field, the fine structure dominates and the Zeeman effect can be treated as a perturbation. And in the intermediate Zeeman effect, however, you need to consider both of them to be in equal strength, and you will need to go into degenerate perturbation theory, which we'll see a little bit. Alright? Okay. So let's start with the weak field Zeeman effect. And essentially, not to go into too much detail, but from first, just taking the first order correction from perturbation theory, the correction goes to this energy level. Now, the problem is figuring out this guy right here. We know that all right. We know that L plus 2s is nothing but J plus S, but this doesn't give us any information about the expectation value of S. So the way we would look at this is, first of all, in the weak field Zeeman effect, we have to think about which Casimirs matter and which Casimirs don't, just to sort of connect to the previous lecture. Because at the end of the day, it's only about there are only certain quantities that are conserved in certain situations, and in this case, since the fine structure dominates, the conserved quantum numbers are n, l, j, and mj, not ml and ms, and this is basically due to the spin orbit coupling that is visible here. Right? So due to this, we know that j plus s is conserved, but you should know that L and S are not conserved individually. So what happens is L, the time average of S, is simply just a projection of it along J. So you can think of J as a vector, and J of a vector composed of adding the two vectors L and S. And if you want to think about the time average of S, it's basically a projection of S onto J. It's basically this projection. Alright, so basically they precise about a fixed orbit, total angular momentum, and you can find the time average by projecting this here. And when you project this, you get something of this kind, you know, if you just do some algebraic manipulation, you will end up here, and these are essentially our Casimirs, and obviously they will point us automatically to our eigenvalues, and that's what we've done here. Express these in terms of their respective eigenvalues. Right. So from that we can now make a substitution, and we will get this term right here. Just to throw in, and this term in the bracket, this guy right here, it's called the Landau G factor. It's denoted by Gj. So whenever you see Gj in the next upcoming sections, you should know that it's just this term right here. And if we choose B external to be lying along the z-axis, then your EZ just collapses to this simple term. And your mu B is nothing but we're technically just trying to account for the very small internal magnetic field. So that's this guy, and this guy is called the Bohr magneton. Alright, so this is the weak field Zeeman effect, and essentially just to put up a small example in the ground state, you would split it into these two energy levels, and they would split into two distinct lines that are even symmetrical because of just the way the MJs work. And you can see that right here. So if I have a plus MJ, it's going to go this way, and if it's a minus MJ, it's going to go this way, and this will have they have identical slopes as well in this plot. So yeah. Next is the strong field Zeeman effect. Well, here the Zeeman effect dominates, fine structure doesn't. So yeah, so we'll start with the Zeeman Hamiltonian as usual, and the unperturbed energies here, just extending upon the Hamiltonian, would be this guy. However, this is what we would get if we ignore the fine structure completely, but we need the fine structure as a perturbation. So again, going back to perturbation theory, just the first order correction would be this guy from the fine structure. This is a contribution from fine structure, and so yeah, we will also need to count the relativistic contribution from the spin orbit coupling as well. But since we've only caring about the spin orbit coupling along the z-axis, the rest of the guys go to 0, and we are only going to care about the eigenstates of the spin orbit coupling along the z-axis. And when we sort of substitute this under the previous equation, voila, we get this. And the total energy here is basically the sum of both the Zeeman part and the fine structure contribution. Now here's where the real trouble comes in. The real trouble is when you're gonna put both of them in the same footing. So how do we even start this off? First, as always, we'll start with the Hamiltonian, but we can't treat one to be in the first footing. We'll have to consider both of them on equal footing. So this is where we sort of have to go with very, very difficult pieces of computation, as we'll see. Essentially, these states are characterized by Lj and Mj and L. So we use those characterizations, because if we do use L, ML, and MS, what happens is that it makes the matrix elements of Hz a lot easier to deal with, but HFS a lot more difficult. So we're gonna have to come to a middle ground here and see which is easier to deal with, and sort of run with this. And just sort of a throwback to the last lecture, we'll be using the Klebsch-Gordon coefficients to define them as a linear combination, and we'll take the two states which are L is equal to 0 and L is equal to 1. So L is equal to 0, you have these guys, and L is equal to 1, you have these guys. and we essentially take all of these to be the basis of the matrix, and essentially thus the matrix becomes mostly a diagonal one, as we'll see. However, we all the non-zero elements of the fine structure go right into the diagonal, but the Zeeman corrections come in blocks. They are non-diagonal elements. So the complete matrix is a lot more complicated. You know, just like this, as I'll show in the next slide. But you know, the eigenvalues are the same, independent of the chosen basis. All right, it doesn't really matter. But essentially, we are going to try to compute eigenvalues in this basis setup. Okay, so it's a pretty complicated one. It's an 8x8 matrix with a few non-diagonal elements as well. But essentially, we can break it down. This is what gamma is here, and this is what beta is. They are not your usual elements from SR, but they're rather something different that we've just defined for the sake of the matrix. And okay, so just to sort of walk you through, the on-diagonal elements are all, as said earlier, they're from our fine structure, and these guys are from, you know, this guy are from our Zeeman effect. Well, essentially the eigenvalues are the eigenvalues for the excuse me for a moment. Forgive the interruption, guys. Well, as I was saying, the first 4 eigenvalues actually are just displayed along the diagonal, and we only need to figure out the eigenvalues for these blocks. That's the real trouble. But as I said before, they're not too much trouble when we compare them to the other set of bases we could have chosen. So now what we'll do is we'll go ahead and compute the characteristic equation for the first of the 2x2 blocks, and this is the characteristic equation. You solve this quadratic formula, you get these eigenvalues. Well, this is just the first guy, and the second guy would just have a different beta sign. Okay, so they're pretty similar in the sense that you get this guy, you get the other one for free. So we have chosen a good basis actually, and we can solve these energy levels, and we can list them out in the table, and we can plot them out and figure out how they look. And you know, after all of this ridiculous amount of calculation, we do actually end up with the exact same kind of splitting that we're looking for. So this is the different n equal to 2 states of hydrogen with the fine structure and the Zeeman splitting taken into account. When you plot it with all the 3 combined, which is weak, intermediate, and strong, which is to say that, you know, this is not the this is not the Zeeman effect. This is this dotted line is the fine structure, and this is the Zeeman effect with the fine structure. So as you can see, there's a noticeable shift in the energy level, and the shift diverges as we go from weak, intermediate realm to the strong realm. So yeah. Now I'll move on to hyperfine splitting, which is yet again another interesting phenomenon. Well, hyperfine splitting is based on the idea that, you know, even electrons have a small magnetic dipole moment, and so do electrons. So what happens there? Well, the hyperfine splitting is, as the word might have implied, is just a more complicated correction that we're adding to our fine structure at the end of the day. So first we'll start with the dipole moment of the proton, and this is the dipole moment of the electron, as we've seen before. And classically speaking, the dipole sets up a magnetic field. Again, I'm not going to go into any SR here because technically speaking, hyperfine splitting is just a classical phenomenon. So this sets up this magnetic field, and when you want to look at the Hamiltonian, you have to consider this magnetic field as well. So your Hamiltonian becomes this really, really insane thing, because you've just plugged this guy into the fine structure Hamiltonian, essentially. And the first order correction to the energy is basically the expectation value of the perturbing Hamiltonian. So you get this guy here. And well, what happens after this? In the ground state or any state at which L is equal to 0, the wave function is, you can say that it's spherically symmetric. So the first expectation value actually vanishes. Alright, that is only if you're considering the ground state which is spherically symmetrical, or any other state that's spherically symmetrical. Meanwhile, from the Schrodinger equation in 3 dimensions, you find that the stationary state is just given by 1 by pi a cube. So you can just substitute that. So our ridiculously complicated equation that literally pushed this numbering aside is transformed to something much simpler if you make 2 assumptions. Well, this is the ground state, and a different phenomena occurs here actually. So this sp.se is quite different from the s.ls that we saw. So this is actually called spin coupling, not spin orbit coupling, because it involves the dot product of 2 spins in contrast with s.ls. And in the presence of spin coupling, well, your individual spin angular momenta are no longer conserved. Rather, it's the total spin that is conserved. All right. So again, we square this out to find the respective Casimirs, and the S squared is just the total thing. But we know that the electron and proton both have a spin half state. So if you want to look at its eigenvalues, you will end up with 3 by 4 h bar squared. However, in the triplet or parallel spin state, as Rishi mentioned, the total spin is 1. Hence, S squared actually gives us 2 h bar squared. In the singlet state, the total spin is 0, therefore S squared is equal to 0. So, yeah. So, spin coupling actually, what it does is it breaks the so-called spin degeneracy of the ground state, which is to say that different spin states having the same energy level, no more, because here it's not about spins being conserved in individually, it's about the total spin being conserved. So you can actually consider this analogous to when we were talking about total angular momentum, which includes the orbital and the spin being conserved. So you can think of this as a sort of precession in that configuration space. And when you do the energy gap calculation, it's essentially given by this number right here, and you find this here. Well, you might ask, why is all of this so interesting or important? I'd just like to give out one example based on hyperfine splitting. Well, this delta E is very interesting to us, because if I just take this and try to calculate the frequency, it's 1420 megahertz, and interestingly enough, the corresponding wavelength is 21 centimeters, and I hope this rings bells, because 21 centimeters is a form of radiation that falls in the microwave region, and it's actually very, very important for astrophysics. And you might ask why it's interesting. So just to sort of give you a brief, the 21 centimeter line actually offers advantages over the optical realm, because when you are observing galaxies in the through an optical telescope, let's say, you're going to be observing stellar sources, okay? But whereas the 21 centimeter line actually tells us about the gases that are there in the galaxy, okay? So if you can find out the total flux of radiation from the 21 centimeter line in your telescope, and if you know the distance to the galaxy, you can compute exactly the mass of neutral hydrogen in that galaxy, and the gas mass can then be used to compare properties across different galaxies, and you can then start looking for correlations. And yeah, so this gives us extra energy essentially just from one singular parameter about the gas content and the amount of neutral hydrogen. So yeah, with this I'd like to hand it over to the next person, Meenakshi.
Yeah, thank you, Pugal. So, hello, y'all. I'll be talking today about Positronium and Quarkonium systems. And before I start off, I'd like to tell you guys that I don't be going too deep into Positronium and Quarkonium systems. Just the basics, just like everyone else is covered. So, without further ado, I'll start off. The next slide, please. Yeah. Okay. So, what exactly are ONIM systems, you might ask? So, basically, they consist of a particle and an antiparticle, mainly, and this would result in them being annihilated. But they exist long enough for us to make for us to do spectral analysis and come up with results. And one of them is a positronium, which consists of an electron and its antiparticle, which is a positron bound together. And there's a lot of similarities between hydrogen atom and the positronium, which I'll get to in a while. But as I said earlier, they annihilate each other to produce 2 or 3 gamma rays, and this depends on the spin states. We'll mostly be looking at the spin number being 1, but yeah. Also, we would see, like I specified before, the energy levels are very similar to that of the H atom, but there are a few differences which I'll get to in a while. And one of these differences being it consists of 2 particles of equal mass, and there's no center right here, but versus a hydrogen atom where you'd have a proton with a proton in the nucleus with an electron revolving around it. So next slide, please. Okay, and the spectral lines are divided into half right here, and over here we have a picture of a positron and electron, and this is a very simple representation of a positronium system. So yeah, the next slide. Yeah, we can get to representing the positronium's energy levels right here. And first we will represent this in a one body system, which is given by the obvious classical mechanical equation, where the reduced mass is given by m1 m2 divided by m1 plus m2, and the Hamiltonian can be given by the equation which is down here, where h is equal to p1 square by 2 m1 plus p2 square divided by 2 m2 plus v r1 r2. And this is like, of course, like it was stated earlier, Hamiltonian is basically the representation of all energy in the system. So if the potential is dependent only on the separation distance, where r is equal to r2 minus r1, and we work with classical mechanical system where p1 is equal to minus p2, the p being the momentum here, we would get the Hamiltonian into this reduced form down here, which is basically equation 81, p square by 2 mass reduced plus vr. And yeah, this is basically the one body form of the Hamiltonian equation. The next slide, please. Yeah, and r is the distance between m1 and m2, and we're considering this as a single particle right now to simplify stuff. And this equation which I showed you about is unperturbed. If I'm not wrong, Rishi had covered this earlier, and he spoke about what perturbation was. It's more of an approximation based on a value, a simpler answer that we have. The exact value of simple answer we have, we reached an approximation that's perturbation. And this equation that we have seen so far, it's all unperturbed energy levels for the positronium. And like we said earlier, the spectral lines are reduced to half, and since there is not the proton, which accounts for a lot of mass, the mass is divided by m divided by 2 in the Bohr, and we substitute this in the Bohr formula. If you notice, Rishi had spoke about this in the previous slides, and yeah, we basically substitute everything that was applied for the hydrogen atom, keeping in mind that there's a major difference of the total being half of whatever was there for hydrogen, and we get the energy levels of positronium equal to the half of the energy levels of the hydrogen atom, and this is the equation we get. Everything else is same except for 1 divided by 4n square, versus in the hydrogen atom will be 1 divided by 2n square, and n right here would be 1, 2, 3, and we keep going on. And you'll see how n just follows a certain sequence right here. I'll get to that in a while. Next slide, please. Yeah, okay. And of course, Bohr's radius, which is given by 1 by m, is doubled. I mean, it's quite obvious because mass right here is halved, and therefore the radius will be doubled. So the radius of a positronium would be 1.06 into 10 to the power of minus 8. And this is basically the unperturbed equation. But, if we apply the perturbation, basically, if, basically, if we are looking at the relativistic correction to the Hamiltonian, right there, which Rishi had spoken about earlier too, it's what we get right here. Delta H, the relativistic correction of the Hamiltonian would be, we're considering the two of the mass. Okay, yeah, sure. So this is the slide we were at, right? And yeah, I was talking about the relativistic correction of the Hamiltonian applied to both the masses, basically the electron and the positron in the system. And we get the final answer to be minus 1 by 4 m cube c square p4, p to the power of 4. And there's one notable fact. Next slide, please. Yeah. The expectation value of p to the power of 4 in the hydrogenic state would be mc the whole to the power of 4. Basically, the wave function is given by that. And considering everything like becomes halved for a positronium due to the mass, it would be reduced by 1 by 2 to the power of 4, and therefore the relativistic correction would be 1/8 that of hydrogen. So yeah, it's nothing complicated right here. Comparatively simple. It's just arithmetic right here. And the hyperfine splitting, which we were dealing with earlier, would be of the same order as the fine structure, which would be a to the power of 4 mc square. This is because of the mass ratio suppressing the proton spin effects in hydrogen. And it's the same in the positronium. So we would have like pretty much the same structure, but there's a small correction, although this is negligible, which I'll get to in a while again. And since the nucleus is not stationary exactly, we're working with truly static potential. It's just two, systems, it's basically just a system of two particles. And yeah, there is like a correction which we will get to, like I said earlier. Yeah, next slide, please. Yeah, and using classical electrodynamics, we can get this equation right here for H, which has been, the relative form of H, which has been reduced to E square divided by 2 mc square c square into 1 by r into p square plus p into r cap to the power of 2. And this contribution is also in the order of, the same as a to the alpha to the power of 4 mc square. And putting all of these together, we finally get the energy level of a positron to be this equation 86 right here. And the value of epsilon for a singlet spin combination would be 0. But if you're going to consider triplets, if you're going to consider for a triplet contribution for angular momentums varying values, like for instance, if I take j is I've not mentioned it right here, but nevertheless I'll get to it. If j is equal to L plus 1, we would get minus 3L. The value of epsilon would be 3L minus 3L plus 4 divide the whole divided by 1 plus L into 2L plus 3. So that will be for j is equal to L plus 1. And for j is equal to L, you would have 1 by L into L plus 1. And for j is equal to L minus 1, you would have 3L minus 1 divided by L into 2L minus 1. So that's basically for triplets. And as for the next one, I'll continue on. I will like to add a little bit of a fact here, that when the proton spin contributes only to hyperfine level, we use J for the sum of the electron spin, and orbital angular momentum J is equal to L plus S, S, which is the proton spin right here. And okay, that's about it. And also, if you notice, the lamp shift is of the order, you wouldn't know this actually, but the lamp shift of the order is alpha to the power of 5 mc square. It can make a correction to this, but this is already broken the fine structure level in the positronium, so it's kind of negligible. And yeah, next slide, please. Yeah. And for, like I said earlier, this is a very unstable system. An ODM is a very unstable system, and a positron and a positron electron being in the same system obviously annihilates each other, and this would result in the formation of 2 or 3 gamma waves, or basically photons being emitted. And we should it requires that the electron and the positron should coincide, and the perturbation is proportional to the absolute value of psi naught squared. And this only occurs when the angular momentum L is equal to 0. And yeah, as for the next one, the end is, and sorry, the previous slide I was not talking about the. Yeah, okay. Since photon carries the spin 1, this phenomenon only happens in triplet configuration, and this annihilation energy is given by 8 alpha to the power of 4 mc It's not G, it's J, my bad. L given by spectroscopic notation. S for L is equal to 0, P for L is equal to 1, D for L is equal to 2. And S right here, which is in this power right here, is 2. It'll be the total spin. So 0 for singlet and 1 for triplet. So that the 1 right there plays a huge role in determining how the angular momentum works, and the value of epsilon itself, which we've seen in the final equation. Next slide, please. Okay, so we can I'll explain a little about this. As in, like the case of hydrogen, a positron can make transitions from like one state to another with the emission and absorption of a photon, because it's not as limited as hydrogen. And I mean, it's a lot more complicated, definitely, but based on what you've seen, it's a very unstable system and doesn't last for a long time. So all these factors actually contribute to it being very like completely different from hydrogen. And positroniums can disintegrate completely, and it produces 2 or 3 gamma rays, basically photons. the charge conjugation would be -1 to the power of L plus S. For n photons, it would be the charge conjugation number would be -1 to the power of n. And yeah, so I guess that's about it. I would show you the I'll show you the spectrum binding energy graph next after the slide, and the 2-4-2 annihilation cross section for a low relative velocity O, and like the singlet configuration would be sigma is equal to 4 pi alpha square into h square divided by m square CV. Be gamma is equal to sigma. We apply sigma right here. V into psi naught square, which is basically the what the perturbation is proportional to. And if we hello. Okay, can you hear me now?
Yeah, you're audible.
Okay. Where was I exactly? Where did I get cut off actually?
You just got cut off, like, I guess, like 5-10 seconds ago.
Okay, just give me a minute. Okay, cool. Where exactly was I explaining actually?
You asked us to go to next slide, Ra.
Okay, cool. Yeah, so yeah, it's just talking about decay rate and how it is expressed in terms of the hyperfine conjugation. Yeah, so next slide please. Yeah, okay. So yeah, the lifetime is basically the inverse of the decay rate, and it is given by 2h. It's basically the inverse of the same equation with a few changes, of course. And yeah, the next slide please. Yeah, and this is basically the states. If you noticed, I had earlier talked about ns being equal to, like, sorry, the the state being labeled as n to the power of 2s plus 1 lj, right? So when that is applied right here, we get these states. Like for 1s states, we get 1 and 2, and how they are they expressed in terms of electron volts. You would notice this before I get to quarkoniums. I will mention that positroniums and positronium actually provided a very good base for us, deriving, like, if being able to find the states of quarkonium, particularly a charmonium. So yeah, next slide please. Yeah, so what a quarkonium is basically flavorless meson with its constituents are a heavy quark and its anti-quark, and it's a neutral particle. There's a neutral particle and an antiparticle of itself, and we have some examples of quarkonia, which are the J by psi meson and the gamma meson, which are charmonium and bottomonium respectively. And charmonium is basically from a charm quark. This might be a little different, but I'll explain what a charm quark is. And and uh, and a bottomonium, which is basically the form of a bottom quark and its anti-quark. The top quark can't necessarily exist. Sorry, next slide please. toponium. Basically, the high mass of the top quark makes sure toponium doesn't exist, and it decays through an electroweak interaction before even the bound state is formed. And so will only be dealing with charmonium and bottomonium, and we won't really be giving much of emphasis to lighter quark and anti-quark states, because light quarks are kind of intrinsically relativistic, and this is we deal more with a non-relativistic quantum mechanics. So I will explain the others next. So I'll explain about how we can't exactly take hydrogen and whatever we did with hydrogen and positronium into quarkoniums. Next slide, please. Yeah, okay. So yeah, like I said, can we apply this to mesons? Not exactly, because there are a lot of contradictions that counter this, and the forces at work for quarks, they're very strong, and for hydrogen or positronium, they're quite easy, like electromagnetic force. They're like weak forces. So we wouldn't know what potential to use, or how we would use Coulomb's law, and what analog we can apply. But we can make some assumptions based on quantum chromodynamics and quantum electrodynamics, which is basically what the subject of dealing with these onium systems is called. Chromodynamics has more to do with color, and as we know, quarks have a certain state of color, and that is very influential by this. Gluons basically have color and all those factors. And yeah, I will explain about how we can make some assumptions and get to it. And gluon and photon are like massless spin one particles, and the interactions are identical with a difference in the coupling constant alpha s, and they're like color factors for gluons. So based on these, we can make some assumptions that quantum chromodynamics also works in a similar way, and we can reach to the point where at short range we can expect a Coulombic potential where V is approximately equal to 1 by V is proportional to 1 by R, and is the fine hyperfine structure would be similar to that of hydrogen and positronium. And if we have large distances for quark confinement, like, because we would, I mean, it's kind of known that quarks would interact at even large distances. So yeah, the potential must be increasing, but we won't get to explaining all that, and instead I will be showing you this equation, which where v of r is equal to minus 4 by 3 alpha s, which right here is the overall coupling constant, h bar c divided by r into f naught r. Yeah, next slide, please. And before I get to explain what how light quarks are relativistic, I will tell you that alpha s is the chromodynamic analog to the fine structure constant, and 4 by 3 is an appropriate color factor. And F naught is about 16 tons. Attract one each other with a force of like 16 tons. So F right here is the force, and regardless of how far apart they are. But in this, we are considering a closed system. But this is what I meant earlier when I said quarks can come together no matter what distance they are set apart by. And like this is probably why it's so difficult to work with quarks, and how this is still a continuing field of research even many years after we finally figured out what quarks were. And light quark mesons are relativistic, and everything we've been dealing with so far, like I said earlier, was non-relativistic. And the Schrodinger equation, which we started off in the middle with, was relatively it's not relative at all. So we would have to consider that splitting is like the relativistic bound state problem. We don't have it right now, and heavy quarks, a non-relativistic theory works well. And since we are quite far apart from getting all these into practice, So we know this much about non-relativistic things, and now we are able to get it for heavy quarks. So we can find the binding. We can find the total mass given by m1 m2 plus E by c square, where the binding E is the binding energy and c square, yeah, of course, speed of light. Shortly before, and yeah, we can here. I'll explain how there was a similarity between charmoniums and positrons, and how charmoniums were discovered. So before the discovery of psi, scientists Politzer and Appelquist suggested that if a heavy charm quark existed, it would form a non-relativistic bound state, Cc, with the spectral levels similar to positronium. So yeah, this is where there's a similarity between positronium and charmonium. So a charm quark, this was considered a charm quark before psi was discovered. And next slide, please. Much after psi was found, it will discover that the 1 cube S1 state, basically the same formula we used for positroniums, that was the state of charmonium, and we could derive it further using the same formula. Like this is like the lowest level state is not exactly the ground state, so we consider we since there's a similarity between positronium and charmonium in this aspect, we kind of derive the graph from there, and it pretty much looks the same. And yeah, right here you have the Boyle's energy levels. You would notice that it progressively increases for each energy level, and for annihilation through a virtual proton, it has to carry a spin of 1, and you could, yeah, like I said earlier, this is not a ground state of charmonium. And yeah, next slide, please. Yeah, actually, next slide. I skipped the slide. Yeah, okay. So this right here is the charmonium slide. Like if you remember the positron graph, you notice a lot of similarities in state, except that you also have quasi-stable states up here. So you would have the 3 cube S1 state, for example, is a quasi-stable state, and everything else below that is stable states. And the previous slide, actually. So yeah, bottomonium. So how did we get to bottomonium? That's quite relatively new. And yeah, Ashwin and Gottfried predicted that bottomonium would exhibit bound states even richer than charmonium. And we considered N1, N2, N3 levels also being bound, because it was a prediction based on experimental values we got for charmonium and considering how the bottom quark behaved. So the epsilon meson was discovered, and this was said to be the 1 cube S1 state of bottomonium. And yeah, so yeah, can you go to the next slide? The slide after that, after the next slide. Yeah, so this is basically the graph for bottomonium, and you'd notice that there are some similarities to what we'd seen in the spectral levels for charmonium, but there's some differences too, where we have much more levels right here, and the quasi-bound states only go beyond when n is equal to 4. So yeah, that's basically how we arrived at charmoniums and bottomoniums. And these were all quarks. So yeah, basically this is how we got charmoniums and bottomoniums. Basically, if I look back at it, this was quite recent. So there are a lot of developments happening even now, but there's a lot of developments even after this. We could keep on talking, but this we're dealing, like I said earlier, we're dealing with more of an intro level thing right here. I'm not delving deep into this. So I think this is where I finish, and I'll hand it over to Gavin for talking about light quark mesons. Thank you.
Yeah, okay. I'm going to be talking about light quark mesons. Okay, so mesons are subatomic particles that are made up of both a quark and an antiquark. Okay, so light quark mesons are made up of the three lightest quarks. Next slide, please. So the three lightest quarks are the up, down, and the strange quarks. The quark spins are either anti-parallel or parallel, where s is equal to 0 or 1 respectively. So those configurations give the pseudoscalar and the vector mesons. So pseudoscalar mesons mean that the parity is odd, but the spin is 0. And vector mesons mean that the parity is odd and the spin is 1. So parity has already been discussed by Rishi during the last lecture, so we'll skip that for now. Down below, you can see the pseudoscalar nonnet and the vector nonnet, which shows all the light quark mesons in it. Next slide. Okay, so we combine 9 quarks just by combining a quark and antiquark in all possible combinations, but we have 3 neutral states that has strangeness 0. So these are pi naught, eta, and eta dash for pseudoscalar mesons, and rho naught, phi, and omega for vector mesons. So we'll go more into that later, but for now, the up and down quarks represent an isospin doublet. So an isospin doublet basically means that the two groups that form an isospin doublets can be transformed into each other when the SU2 group transforms. Okay, the antiquarks also constitute an isospin doublet. Next slide. Okay, so when we combine two particles with I is equal to half, we obtain an isotriplet and an isosinglet. So you can see these values here, the 3 isotriplets and the 1 isosinglet. Next slide. In the case of pseudoscalar mesons, the triplet is the pi naught meson, and for vectors, it is a rho naught mesons. The interesting thing is, for both the pi naught or the rho naught mesons, they take only the linear combination and not the UU dash or the DD dash. So the pi naught or rho naught is equal to UU dash minus DD dash by root 2. Next. Okay, but this leaves eta and eta dash or omega and phi, depending on whether it's pseudoscalar or vector. And these are given by the two I is equal to 0 states, the isosinglet combination and the S dash states. So in the case of pseudoscalar mesons, eta is equal to UU dash plus DD dash minus 2 SS dash by root of 6. And eta dash is equal to UU dash plus DD dash plus 2 SS dash by root 3. And in the case of vector mesons, it is UU dash plus DD dash by root 2, and phi is equal to S of S dash. Okay, next slide. So strange mesons are constructed by combining an S quark with either a U or D quark, both the quark and the antiquarks. So you can see K plus, K naught dash, and K minus given there. Okay, so the 3 light quarks belong to the group SU3 and are denoted by 3, and the antiquarks belong to the same SU3 and are denoted by 3 dash. So when we combine these representations, we obtain an octet and a singlet. Okay, so next slide. If it were perfect symmetry, then all the particles would have the same mass, but they do not. We know that K weighs more than eta, and this is because the S quark is substantially heavier than both the up quark and the down quark. So as a result, the K meson weighs more than the pi meson. But this can't be the only reason why, because if that were the case, then the rho mesons would weigh the same as the pi mesons, since they have the same quarks and the same energy levels. Next slide. So the only difference can be that the relative orientation of the quark spins are different. For pseudoscalars, it's 0, and vector mesons, it's 1. So the difference in mass must be because of the spin-spin interactions. This is a QCD analog to hyperfine splitting of ground state of hydrogen, from which we get the meson mass formula. M is equal to M1 plus M2 plus A into S1 into S2 by M1 M2. So if we square S is equal to S1 plus S2, then we get S1 into S2 is equal to half of S square minus S1 square minus S2 square, where which is equal to H cross square by 4 for vector mesons and minus 3 H cross square by 4 for pseudoscalar mesons. Next slide. Okay. Now, if we substitute the values of mu and md, which is equal to 308 mega electron volts by c square, and ms as 483 mega electron volts by c square, then the best fit value for A is 2 mu by h cross, the whole square, into 160 mega electron volts by c square. Next slide. So here you can see some of the meson masses for the pseudoscalar and vector mesons. As you can see, the calculated ones are extremely close to the observed ones, although not completely accurate. Okay, next I'll leave it to Ashwin to talk about baryons.
Okay, it's already very late, so without any introduction, let's directly dive into baryons, their masses and magnetic moments. Well, baryon is a type of composite subatomic particle which contains three quarks. Baryons belong to the hadron family of particles. Hadrons are composed of quarks. If you have attended the laws structure in high energy physics, you would have known this because baryons contain three quarks from either of the three generations, and mesons have a particle and antiparticle pair, which is only contains two quarks. Baryon has three quarks. And explain. It is the eightfold way. Eightfold way is the way in which baryons are arranged in an orderly fashion. It is similar to a periodic table where all atoms are arranged in accordance with their properties. In periodic table, all atoms are arranged with respect to their acidity, baseness, and metals are grouped into one single section, and every its arrangement shows its properties. Like in the same way, in particle physics, we have a arrangement for baryons and meson. These are known as baryon octet, meson nonet, and baryon decuplet. Next slide. First, let's see baryon octet. This is simply a hexagon with two particles in the middle: neutron, proton, sigma particles, lambda particles, and xi particles. Sigma particles are nothing but two quarks from first generation and one quarks from either of second or third generation, and psi particles are particles with one quarks from first generation and two quarks from second or third generation. The horizontal line in this hexagon denotes the strangeness of the particles. You can ask what strangeness means. It is simple. In Large Hadron Collider or any collider, particles are formed. New particles are formed from high energy collisions, strong interactions, and electromagnetic collisions. But when those particles which are formed from strong interactions they decay into weaker forces. So it's strange, right? It's forming by strong force and it's decaying through weak force, right? This strangeness is named as strangeness. That's all what strangeness means. So horizontal line represents strangeness, and diagonal lines represents the charge in terms of electron charge. Plus 1 means plus 1 electronic charge, and minus 1 means minus 1 electronic charge, and 0 means no charge. Baryon octet has only particles with spin half. Next slide. Baryon decouplet. This is also exactly similar to baryon octet. The horizontal line represents the strangeness of the quarks and the strain of the particles, and the diagonal lines represents the charge of the particles. Uh, during this octet and decouplet was organized by Gilman. When Gilman did this, omega particle doesn't exist. The one in the very bottom does not exist. But he generated this octet and decouplet, right? He said there is a particle which has strangeness free and charge of -1, and it is not discovered yet, it will be discovered. Like he said, it was discovered with the same property. In periodic table, we assume that UU0, UUN will have some this type of property from the arrangement, right? Like that, in this arrangement, from this arrangement, we knew how this particle would be. Now the next slide. Baryon magnetic moment. In the absence of orbital motion, the magnetic moment of a hadron is simply the vector sum of the magnetic moments of its constituent quarks. We are not including the orbital moment here because the equation will get more complicated. So let's just stick around only with the spin angular moment. Mu is equal to mu1, mu2 plus mu3. Baryon of steel particles, right? Those constituent magnetic moments will yield the total magnetic moment. The magnetic moment of a particle charge q and mass m is mu is equal
Try
to
to
q by
encourage
mc
yourself,
into
always try to encourage
yes.
others as well, because encourage is
Rishi
one
have
thing
already
which
explained what
can
is S
give
in
you
equation
confidence, which
41, I
can
think,
take
and
you
Kumar
to
also
another level,
explained. I will tell again, S is
so yeah,
nothing
always
but
try to
J
encourage other
minus L.
women, always
J
try
is
to
the total
encourage
angular
everyone,
momentum, and L
and
is the
never give up and never
orbital
say
angular
like it's
momentum.
not happening
Since we
or it
are
will not happen.
excluding orbital
And
angular
it's
momentum,
okay if you
here
fail,
total magnetic momentum
but
and spin
never give
angular
up.
momentum
Always
are the
try
same.
to learn
Next
from
slide.
your experience why I have
The
failed. Like in
previous
games,
slide we
like
saw that
from me,
mu
I
is
can
equal
say what I
to q by
learned from
mc into
basketball
sa.
is that
That is the
I have learned how to
vector
respect my
product
opponents. I
vector
have learned
equation.
how to
Now
handle
this is
failure,
the q is
and
equal
more
to
importantly, I have
h bar by
learned
2
how
mc
to
is
handle success.
magnitude of that
There are many
equation.
people who cannot
Here
handle
s z
success.
is equal to
Yeah.
h
So
bar by 2.
failure
This
we
is
can,
because we are
yeah.
considering
So
only the
for failure,
baryons
I
from
can
octet
blame
which
it,
has
that
spin
blame, but for success,
0.5.
you cannot blame anyone because you
If we
are succeeding.
included
But to
baryons
maintain that
from
success and to
decouplet, then
stay
this
grounded at
equation,
that
then the
position, it's
value of
very
SZ
important.
will be 3
So
of
yeah,
3
one
h
thing I
bar
would
by
say,
2.
never give up and always
So
look
let's
for
see some
opportunities.
examples.
It's okay if you
You
get
can see the
rejected,
value of
no problem. Just
up quarks
clean
magnetic
the
momentum and
street
down
out and
quarks
walk
magnetic momentum
through
and
it.
strange
Yeah.
quarks magnetic
Amazing.
moment.
That was beautiful and so empowering.
Proton
Thank you
and
so much for joining us, man.
let's say take
Yeah. Thank you
proton.
so much.
Proton has two
And
up
thank you to
quarks
everyone
and one
who's
down
watched
quarks,
us
right?
live
If you
or listening to us
add
in a
these
recorded session.
up quarks
Do
magnetic
join us
momentum
again
and
next
down
week.
quarks
We'll be
magnetic
here
momentum,
every
you
Saturday.
will get the
That.
magnetic
Bye
moment
bye.
of the total proton. Next slide, Ra. Baryon mass. I don't want to read this equation. Just see, this is the equation from which all the mass of the baryons is being calculated. It is the sum of three constituent quarks and one big term. Since the baryon
It
mass is
ended.
mostly due to
Yes, it
strong
ended.
interaction,
Amazing.
we add this term, which is directly proportional to the dot products of spins and inversely proportional to the product of the mass. The term A dash is constant, but it is not fixed. A dash is constant, but it is not fixed. It is adjusted to get the most optimal fit to the data. Next one, Ra. The mass of the nucleon. Here we are taking the mass of up quark and down quark to be same, so such that three first M1, M2, M3 will be the same, so we can put it 3 mu. The value of S in the previous equation we saw S1 S2 plus S1 S3 plus S3 S2 S3, right? Those values, when we calculate, the value for octet will be minus 3 by 4 h bar square, and the value for decouplet will be 3 by 4 h cross square. If we substitute these equations in the first equation we saw, we will end up with the mass of the nucleons. The calculated mass from this equation and the mass obtained from the experiment will differ in a very small value. This is because in the uncertainty of the mass of the quarks, or mass of the quarks, and also due to the uncertainty in the constant, because we are fixing the constant for the optimal fit for the data. It is a constant, but it is not fixed. Okay, that's all. For thank you for listening.